What trait do gravity and electricity have in common? Stay tuned to find out. Hi, I'm Robin DeMarco, the online physics teacher, and my passion is to help take the mystery out of physics and help to supercharge your physics education. I started off by asking the question, what do gravity and electricity share as a trait? And the answer is they're both fields. Now, before we begin, if you haven't already watched my video on electric fields, please take a few minutes, check out the link that'll be up in one of these corners, and go watch that first, because you really need to understand what an electric field is before we can take the next step. Sometimes talking about an electric field can be a little confusing because we don't really have a way that we can see the electric field. We can sense it, we can measure it, but we don't always have a way that we can see it. So what I'm going to do is I'm going to use an analogy. We're going to look at a gravitational field. We'll do that first, and then we're going to apply it, the same concept, to the electric field. Okay, within a gravitational field, when something starts off at ground level, it has zero potential energy. Now, if I pick that object up and I move it up over my head, what's happening is I'm doing work. I'm applying a force over a distance, and I raise that up. Now, doing that provides me with potential energy. Now the object can fall down, it has potential energy. That's really what we want to take a look at today, is how this potential energy is going to work. We can express this in a couple of different ways. First, we could look at it as work equals a force times a distance. That's the definition. We can break it down even further and say that the force, that especially when we're moving something up, the force is mass times gravity. That's Newton's second law, right? F equals ma, where a is the gravitational acceleration. So we have mg, and the distance it's moved is h, the height. Now we know from conservation of energy that the work done moving the object up to that level, that new point, is equal to the potential energy. So if we look at this now from a different perspective, now we're going to go back and look at the electrical, or the electric field. And what we see is that, again, we can have 2 points that are different potentials. When we move points of charge from one area to another, we have to do work on them, which means we have to have a potential difference between those 2 points. And that's where today's video is going to focus. Okay, to take this a little bit further, we're going to go to the whiteboard. Okay, what we see here is we have 2 demonstrations. We have a gravitational field on the left side, and we're going to have an electric field on the right side. Now, what we see in the gravitational field is at the ground level, potential energy equals 0. And as we go up to the height, h, potential energy equals mgh. And we know that anywhere inside this field, that the field is always going in the same direction. It's going to come straight down. Okay, so let's take a look now at our electric field, which is the one over here. Label that. I didn't label that earlier. Now, in one of our previous videos, we talked about the fact that the way we look at the field between parallel plates is we're going to put positive test charges in here, and we're going to see which way the field is going. So in this case, a positive test charge is going to get pushed from the top plate to the bottom plate. So instantly we see we have some correlation here. The direction of the field is exactly the same way. And I moved, in the gravitational field, I moved the object from the bottom to the top. So here we're going to take and we're going to move an object. Let's make it over here. And I'll make it a different color so it will stand out better. we're going to say this is a charged object. So let's say this is an object that has charge Q on it. As we move the charge up, what we see happening here is that we've done work on the charge, and the amount of work per unit charge shows us the potential difference. And that's the first equation we're going to use today. So the work per unit charge is called the potential difference. The unit of potential difference, if we look at it, work is we know is in joules, and charge is in coulombs, so it's joule per coulomb, which we have defined as a volt. Okay, so let's take a look at a quick example here. So we want to know, what is the potential difference between 2 points if it takes 0.96 joules of work to move a charge of 8.0 times 10 to the minus 2 coulombs from one point to the other? So what we're going to start off by doing here is we're going to make sure we actually have a pen. There we go. All right, and I'll do this in blue as well. All right, so what we want to start off doing here is just looking at the equation we just came up with. V is equal to W over Q. So in this case, we have 0.96 joules, and we're dividing that by 8.0 times 10 to the minus 2 coulombs. If you punch this in on the calculator, what you're going to find is we get an answer, 12.0 volts. Pretty easy, pretty straightforward. In this problem, we're asked to determine how much work is done by moving an electron across a potential difference of 1 volt. So again, we're going to come back to set up our equation, V equals W over Q. However, we're looking for the amount of work that's being done here. So I'm going to rearrange my equation. In this case, I'm going to have that work is equal to the potential difference times the charge, which is 1 volt, 1.0 volts, times 1.6 times 10 to the minus 19th coulombs. And what we get here is the work in this case is going to be equal to 1.6 times 10 to the minus 19th joules. This doesn't sound real exciting, kind of an easy problem, right? There's a reason I brought this up. And the reason is this value has a very special name to it. It's used to express small amounts of energy, and we call this an electron volt. And it's represented by 1 eV. So when we talk about things in like atomic physics or nuclear physics, the energy levels will be expressed usually in electron volts. Now let's go back to looking at a parallel plate here. And if we know that if we take an object or a charge and we move that charge from here all the way over to here, we've moved it some distance d. And we've defined that the work that's being done is, we know that work is equal to force times distance. And we also know that from the previous example, it equals V times Q. So what I want to do now is I want to look at these two pieces here. We know they're equal to each other, and I'm looking for a relationship here. So what we're going to do is we're going to divide both sides by D. And then I'm going to divide both sides by Q. So my end result then is I get F over Q equals V over D. Now, the important part about this is to remember that in our previous video, we showed that this right there is actually an electric field. So because these terms are equal to each other, we know that V over D is another way I can show an electric field. So let's finish off our section with one more example. In this example, we're asked to calculate the uniform electric field between two parallel plates that are separated by 2.5 millimeters if the potential difference between them is 50 volts. So I'm looking for an electric field, E, and we know it's going to be V over D. Now, before I can go any further, I need to look at something here. And I'm going to box it in right here. They gave me a distance in millimeters. So I have to convert that into meters. Now, you can do it a couple of different ways. I personally like to use scientific notation. So what I'm going to do here is I'm going to just write it out as 2.5 times 10 to the minus 3 meters. You could also write this as 0.0025, whichever way makes you feel better. Solving our problem here, we're going to have 50 volts divided by 2.5 times 10 to the minus 3 meters. And what we're going to get here when we put this through on our calculator is we're going to get an answer of 2.0 times 10 to the 4th volts per meter. So there we have it. We found another way we can express an electric field. We've also talked about the electric potential difference. I hope this video helped you. If you've gotten any use out of it, please give it a thumbs up and hit the subscribe button. And stay tuned for more videos. Take care.